Good morning, everybody. It is a great pleasure to be here with you and talk about the thing that excites me most, the future of science, the future of space exploration, and inspiring the future generations. Before I jump in, I just wanted to sort of share a couple of thoughts with you. You know, as I stand here and we're together today talking about the future of science beyond the ISS, the impact of cislunar environment, and that sort of broader space policy and commercialization, you know, I can't help but think that we really are at an inflection point. The decisions that we make today will literally shape the architecture and the future of space exploration for generations to come. And as the head of NASA Science, I take this responsibility pretty seriously, both as we drive innovation, but also as we take seriously the stewardship of what we do. We have an extremely broad portfolio. It is the most dynamic portfolio you can imagine. We have amazingly ambitious planetary science missions. We have cutting-edge Earth observation. We have our incredible cosmic voyages peering back into the depths of time. And we have really, really impactful research that we do in our biological and physical sciences, really shaping and doing the work that we will actually need to have a sustained presence in space. So we have this really broad portfolio. We take it very seriously. We use it to drive the innovation. We use it also to ensure that we make sure that space remains accessible, open for everybody. I just want to sort of frame the talk with a couple of thoughts that maybe you can keep in mind as we're having discussions throughout the day. You know, the first one is as we get ready to take these next big, bold steps in space exploration, science is an enabler. You know, as we are thinking about a sustained presence on the moon, as we are thinking of sending humans to Mars and hopefully beyond Mars, space research and science is not an add-on, it is a fundamental piece. Whether you're talking about understanding the harsh radiation environment, whether you're talking about the dynamics of the dust that we have to deal with whenever we land, whether you're thinking about how to keep crew safe on these missions, science is the thing that enables it. Science is exploration. We explore to do science. And that's something that I really want you to kind of just think about as we go through today. Partnership is also a key to science. When we do these big things, we don't do them alone as one government agency. We do them in very close partnerships with our industrial partners, with our academic partners, and with our international partners. And partnership really drives what we do. Also, this sort of, the responsibility and the commitment we have to the broader space commons, ensuring that we enable open access to space. We have embraced open access to science with our programs to make sure that all of our science data are open and available and usable by everybody. And then, the idea that science really has an incredible return on investment. All of the work that we do, whether it's with our partnerships, whether we're putting money into industry to be able to enable these great discoveries, it really does provide a great ROI. Take, for example, our incredible James Webb Space Telescope. Nobody in industry would have done that on their own. If anyone had gone to their board meeting and talked to their trustees and said, hey, I want to build this huge telescope, they would have been laughed out of the room. But because we did it in partnership, we have driven technology advancements. There are hundreds of technology advancements that came about because of the work that was needed to enable the James Webb Space Telescope, things that you didn't even know you needed at the time that we started that mission, driving the latest cutting-edge microprocessors, GPS, your phones, all of the things that you just didn't even think about when we started that James Webb Telescope. And so with that, I'm going to take you just give you some highlights. The thing I love to do the most is talk about NASA science. The challenge for me is staying to 30 minutes because I can do it for about 3 hours. There's so much great stuff going on. And so it's going to be my great pleasure to give you a pretty quick tour through some of the highlights that we have in NASA science. And so to kick us off, our favorite, should be everybody's favorite planet, Earth, the one that we live on, the only planet we know so far that sustains life in the universe. Our amazing Earth observation spacecraft are just doing great things all the time. This is just one example. This is called OpenET. This is evapotranspiration. So this is basically how we measure the soil moisture from space. It's extremely hard to measure soil moisture on Earth, but we use our fleet of spacecraft to be able to do this. This is an openly accessible tool that is used every day by farmers and ranchers to literally look at whether or not they need to water their crops. It allows them to do total water management. Water is our most precious resource here on Earth, but it also not only enables them to know exactly when to do the watering, it is actually dramatically increasing crop yield. We can actually look and see if the roots are in stress, which of course will decrease the crop yield. And so by knowing exactly when to water, we can actually really increase the profits and the food that we need here on Earth. So this is just one of our examples, many tools that we have openly available to the public. Later this year, we will launch NISAR. NISAR is our first major partnership with the Indian Science Research Organization. So this is, NISAR is NASA ISRO Synthetic Aperture Radar. We love our acronyms. This is a very unusual looking spacecraft. The top there you see is it's a bloomed synthetic aperture radar. That structure is about 39 feet across, so it is extremely big. NISAR, when it is launched later this year, will allow us to basically look at the Earth's ecosystems, look at things like ice sheet formation, glacier formation, melting, looking at things because of its incredible accuracy and resolution. We can look at things like fields, small localized fields and how they are faring to large scale things. It's going to allow us to look at intense weather events just by looking at all of the pieces of the puzzle with these. It's actually got two radars, two different bands of radars, allowing us to look kind of at different heights. So one really focused on peering through the clouds, another actually being able to go beneath the canopy of a lot of our forestry and looking at where we have like deforestation, and where we need to actually go and focus on doing more crop growth, and also where we may need to do targeted wildfires to get rid of some of the dead brush to be able to replenish our forests. So that is NISAR. Again, looking forward to that launch. So on to planetary science. You may have seen recently we started revealing the secrets that have been unlocked by our OSIRIS-REx mission. OSIRIS-REx returned samples from an asteroid called Bennu. They came back to Earth in September of 2023. And we immediately started looking at what was in those samples. We recently released that we found in just this one tiny sample from this asteroid that 14 of the 20 amino acids and all 5 of the nucleobases, that make up all DNA here on Earth are actually present in that sample, which is amazing. We also found that at one point there was like a saline atmosphere, so you can almost think of it like a sort of broth that you could mix these various amino acids and bases in to actually start life. Now, there's no sign of life in these samples, but it is interesting as you think about, these are very old asteroids. They were around at the time that our solar system was forming. They have the building blocks of life in them. Why didn't life start on this asteroid? Why, what was it? What was different here on Earth that caused life to start here? Just really fascinating questions that we think about every day, but also shows the power of when you can bring samples back to Earth. We We brought samples back throughout the Apollo missions. When we first had those samples here, we had very rudimentary equipment that we could use to study those samples. Now we study those Apollo samples with mass spectrometers, the size of like your living room, allowing us to really look in a very, very different way at those samples. Also talks about why we're very passionate about saving a lot of the samples. About 25% of the OSIRIS-REx samples will be opened and studied now. The other 75 will be very carefully curated for future generations, again, to allow open access to science and sharing the joy with generations to come. Okay, NEO-Surveyor. That's the first time I've seen that image, and that's not the normal NEO-Surveyor chart for me. All right, so this is NEO-Surveyor getting ready to go into, actually in the historic chamber. So this is at the Johnson Space Center, their Chamber A, where they have done all of the really big missions have been tested in this chamber. But NEO-Surveyor will launch 2027. And it's just finished its critical design review and started its environmental testing. It is charged with finding near-Earth asteroids, near-Earth objects. It is going to be looking in the near-infrared, and so it will allow us to look at dark objects. So a lot of these asteroids, they don't really emit in the visible light, but by looking at them in infrared, we'll actually see kind of the heat signatures from them as they get close to the sun. So it's allowing us to see in a different way what we can't see with our ground-based instruments. It also allows us to look much closer to the sun. Obviously, we can't look right at the sun, but we can look much closer to the sun and see these near-Earth asteroids. The idea is that we catalog every asteroid that could be a problem for us here on Earth. All right, I have to unashamedly say this is kind of my favorite mission. This is Dragonfly. Dragonfly is going to launch and go out to a distant moon, Titan, so it's a moon of Saturn. It is a fascinating place. We believe that Titan is the most like Earth in the entire solar system. It literally has mountain ranges, it has deserts, it has a cycle, like we have a water cycle here on Earth, they have a methane cycle. So there are literally like pools of methane. You can imagine this thing sort of flying over, it'd be like taking postcards and taking images of what this distant place looks like. It is also thought to be a place that also could have the building blocks of life. We know there is methane, we know there are long, complex carbons basically laying on the surface there, and so going to study again, what was the ancient solar system like? What were the conditions like before life started here on Earth? It's something we continually want to study. We launched Europa Clipper last year, going out to the moon Europa, excuse me, where we think better. I didn't want to do that into the microphone. We're looking again for these signs of building blocks of life. Once life formed here on Earth, we're really kind of noisy. We sort of covered everything with signatures of life. It is extremely hard to actually think about what this planet was like before life started, because we've literally invaded everything. So by going to Europa, by going to Titan, by bringing samples back from Mars of really ancient rocks, 4 billion-year-old rocks, looking for what were the conditions like here on Earth. Dragonfly, just the technology behind it, it's about the size of an SUV. It is an octocopter, and so it will be a powered flight mission. It will come out of its aeroshell, go immediately into powered flight, land on Titan, take lots of data, and then fly to another location and do this over and over again, allowing us to explore this incredible moon. So continuing sort of with the planetary science theme, but really focusing on our exploration and our support for Moon to Mars. This is our commercial lunar payload services. program. Many of you, I know, have interests in this, either through instruments or even part of building the landers. We have launched 4 so far. We had one totally successful mission earlier this year, the Blue Ghost mission from Firefly. You're looking there, it had a very novel sort of technology demonstration on it that was built at the Langley Space Center. And looking at this, looking at kind of the plumes that are formed as the lander was coming down. You've got these large engines that are helping you land, but obviously you've got a lot of dust and regolith that gets kicked up when these when this is happening. As we think about building up a sustained presence on the moon, and we think about, you know, landing sensitive equipment, you're going to bring down, you know, more and more landers, you have to understand how the plumes work so you don't literally cover your solar panels of a neighboring thing with dust. We know that the dust is very tacky from the Apollo days. It kind of stayed on everything. It even got into the astronauts' lungs. And so we really need to kind of understand how this regolith is going to react as we land larger and larger landers. Also on Blue Ghost, we had, in fact, an experiment that's sort of studying just how tacky, how sticky that dust is. Also, another one that is looking at whether, you know, when you put an electric current through, will it actually remove any of the regolith, which is really important to us, and a radiation-hardened, radiation-tolerant computer that they were continually causing upsets to happen to see if it could recover in the lunar environment. This is all really important because not only are we thinking about a sustained presence on the moon, but we're also preparing to send crewed missions to Mars. If you think the lunar dust is tacky, Mars dust is even more tacky. If you think of the Ingenuity helicopter, our beautiful little helicopter that flew above Mars, above the Martian surface, the dust and the regolith from Mars built up on those rotor blades. And if you think nothing sticks to a helicopter blade here, as fast as those rotor blades were spinning, the dust continued to accumulate on those. And so we know it's incredibly, incredibly tacky. It will, you know, if you're going to go to Mars, you're going to stay there for a reasonable time. What are the trace elements in that regolith? What are they going to do? Are they going to be harmful for folks? And what are they? How are we going to keep our equipment clean? So really, really important information that we're looking at. Biological and physical sciences, most of our work there is done right now on the International Space Station. We have a wide variety of both biological, looking at like how we grow plants in microgravity. We have tissue chip experiments looking at, you know, how human organs respond to extended stays in space. And we have one of my favorites, the Cold Atom Lab. The Cold Atom Lab, we can using lasers, cool down to less than a degree above absolute zero. When this happens, clouds of atoms form like the fifth state of matter, what we call a Bose-Einstein condensate. That allows, I mean, almost imagine kind of suspending an atom and being able to sort of look around it. We sort of describe it as making those atomic processes macroscopic. So it actually allows you to look and study how atoms work. Because they're in microgravity, we can suspend them for a few seconds and actually do this study. Unlocked so many things that we use every day. This year is the 100th year of quantum science, and Cal really making great strides as we think of like next generation detectors for space, but also GPS, atomic clocks, again, technology that you rely on all the time, made possible by this research that we do on the International Space Station. You'll also notice there my friend Rob Furl, who is our first researcher who actually did his own experiments in space. So he went up on a New Shepard launch. He was a sort of tech demo. You can kind of see there on his legs, he's got what looked like test tubes strapped there. And he was actually looking at how plant genetics vary with different levels of microgravity. So he would sort of, click the top, and the experiment would start at the different altitudes. His partner was down on Earth in a lab very close to the launch site, and they had it sort of timed. So as he was clicking and setting off the experiment, she was doing kind of the ground-based control, so they could actually look at the differences. Also showing, we are really leaning into different ways as we think of beyond the ISS, ways that we can do our science. As we sort of look at commercial LEO, we're really excited about the fact that we could be using commercial science astronauts to be able to do our work. Most of our work just needs to be taken up there and left up there, and we can control it from Earth. CAL, for example, is completely controlled from the Jet Propulsion Lab, or even just this idea of quick refresh. Take an experiment up, leave it there for a few months, bring it back down, we can tweak it, goes back up again. So we're really excited about the opportunity that will unlock for us. And finally, looking at the science that we can do with Artemis. And so we've selected 3 science experiments to go to the lunar surface with the first astronauts. One is called LEAF. It is looking at how we can grow plants in the lunar regolith, really important if you want to sustain presence on the moon. Another of them is basically looking for volatiles. It is LDA is the acronym, and it's basically putting currents through the regolith to see if you can find volatiles. And then the last one is LEMS, which is looking basically at like seismic activity on the moon, how often you get moonquakes. Again, really important. It's almost like the weather forecast. What is the terrain of the moon going to be like today, helping us to sort of understand the dynamics. And I am running out of time. Okay, so onto heliophysics, my former division there. We recently launched the Punch spacecraft. It was actually a ride share. We launched it with an astrophysics telescope that I'm going to tell you about in a minute. This is 4 spacecraft. They're about the size of a checked suitcase each. You can see the first light image there, which, people say, well, it looks really boring, and I'm like, that's actually what you want to see because there's no stray light in it, so we like that boring image. But they deployed. They're still in their commissioning phase. 3 of them will sort of move around to form one big wide-angled imager. The 4th one, a narrow field imager, looking deep into the corona. I like to think of it as sort of looking at the sun from the inside out, looking deep into the corona and then following all of that space weather activity as it comes towards Earth. Parker Solar Probe, can't lie, always will be my favorite mission, Parker Solar Probe. But that launched in 2018. NASA's been studying the solar wind since the early 60s. The solar wind, that sort of connection between the activity on the sun and what we feel here at Earth as space weather effects. Parker recently broke records. It traveled at 430,000 miles an hour. It was within 3.8 million miles of the sun's surface, again, unlocking what is going on in this region that we've never been able to sample before. We've taken images of the sun in every single wavelength. We've sent spacecraft in as far as the planet Mercury, but there was always this region that it's almost like you can't see the wood for the trees. You actually need to get into that region to sample the science that's going on, because you just can't see those processes from further out. And then finishing up on heliophysics, this is a really cute little, I probably shouldn't say cute about a mission, but it's 3 little tiny CubeSats. They're about the size of a shoebox each. They launched actually on a transporter earlier this year. And the 3 of them up in space already. They've had their first look data, their first spectrograph. They're basically looking at like the magnetic footprint of the aurora. So they're in a very unique region where it's too high for our high altitude aircraft to fly through, but it's too low for traditional spacecraft because we would have to keep, station keeping them and keep boosting them up. It's just in this really interesting region where sort of space weather and terrestrial weather meet and mix. And so they are flying through this region of the aurora, kind of understanding the currents to better help us predict how vicious the aurora will be. They look beautiful, but they also cause problems, as you all know, for power grids, for long undersea cables, for pipelines. When you see an aurora, it is an electric current that can really interfere with our technology. So finishing up with astrophysics, this is, I mentioned, we launched Punch as a rideshare. The cake topper on the stack was SphereX. SphereX, looking at the universe in a very different way. It is looking in sort of near infrared, but it is breaking down the wavelengths into very, very, very discrete bands, allowing us to look at a real different range of phenomena, allowing us to look for like water and vapors, and start to sort of be able to figure out what the atmospheres around in our universe are made of. It will, in its lifetime, study about 450 million galaxies, and so that is just less than $1 per galaxy, by the way. So it's very economical. So that's SphereX. Looking forward, also being able to look back in time to just like a picosecond after the Big Bang. So also allowing us to study why our universe expanded the way it did so quickly, and what sort of drove that dramatic expansion. And then finishing up with the James Webb Space Telescope, something that we love to talk about, looking there at a phenomena that was fairly recently discovered, looking at these little red dots, which were very imaginatively named little red dots by our astronomy community. But we don't really understand them. They're unusual phenomena. We don't really understand why they are this color. But as we've started to study them, a large number of them actually have kind of a growing a big black hole in the center of those dots. And the other interesting thing is that they became very prevalent about 600 million years after the Big Bang, and then they kind of stop at 1.5 billion years after the Big Bang. So it's just a really, really interesting phenomena that we recently found with the James Webb Space Telescope. And then this is, I think, probably my favorite image from the James Webb Space Telescope. It's a very unique image. You're looking at an edge on protoplanetary disk, known as HH30. Basically, this is like where young stars are forming. This is a star formation region. As the young stars are forming, they basically let out like jets of gas, and what you're looking at is these jets that are they're made luminous by the shock waves that are around in the universe. The thing that makes this unusual is obviously the star is at one end of the jet because the jet is coming out, but this one, you are looking at the star is actually hidden by the protoplasmic disk there, or protoplanetary disk, sorry. And so it's actually illuminating the whole disk. So you can't see the star, but you can see this incredible view of what a protoplanetary disk looks like. Kind of in the sort of tail over there, that is, there's lots of sort of dust grains there, and they will start to sort of coalesce. They will form small pebbles, and then they will eventually form planets. And so this is, you're sort of looking at, from dust to dirt, from tiny cosmic dust that will eventually become planets around this neighboring star. Okay, and then looking to the future with our Nancy Grace Roman Space Telescope, currently about 90, I think the statistic I saw was 91% complete, and getting ready to go into its final testing, about to go into the vibration testing, looking at a really great shot of it, sort of looking down the barrel of Nancy Grace Roman, so you can actually see the detectors inside. Nancy Grace is going to let us look at dark matter and dark energy in the universe, which makes up the most of the universe. It will study billions of different galaxies, millions of stars, and it also has a tech demonstration with it. So not only is it sort of going to be doing this great astrophysics science, it's also carrying this stellar coronagraph. So you're used to seeing coronagraphs that block out the light of the sun so we can study the corona. This is going to block out the light of distant stars so we can really resolve the planets around those stars, helping us, again, as we search for life elsewhere in the universe. I had one more thought on that one. Oh yes, the field of view of it is about 100 times that of Hubble, and it is an unusual way for us to do science with this this particular telescope. Normally we do what we call sort of point and shoot. You know, you pick your target, you turn your observatory, you take your imaging. This one is a full sky survey, and so it sort of does this kind of bowing motion as it scans the whole sky, allowing us to look in unprecedented detail at our universe. And then this is going to lead us into the Habitable Worlds Observatory, which is the next big astrophysics telescope. Habitable Worlds kind of builds on everything we've done before. It will use the wavelengths of Hubble. It will be a telescope the size of the James Webb Space Telescope, and it will carry the next generation of this stellar coronagraph once we've proved the technology, really now allowing us to peer into the universe, resolve the atmospheres around planets that are you know, close to stars that aren't too violent, that could actually sustain life, and then even allow us to start looking for if there's activity, you know, if there's sort of like, you know, factory activity, anything that's on there, as we continue to look for life in the universe elsewhere. All right, so I'm going to finish by bringing you back to these are our key science themes. We think of these kind of as our North Star. This is what anchors what we do in NASA science. Our overall goal always to protect and improve life on Earth and in space. And we do that many ways through weather prediction, through medical research, through support to our farmers, our fishers, you know, disaster recovery, and, you know, all of the terrestrial weather forecasting, everything that we do to really protect and improve life on Earth and then in space as we get ready for these sustained presence missions going to Mars and beyond. I love to say and beyond. I talked a lot about search for life in the universe elsewhere. We have our astrobiology program that is, you know, things like Europa Clipper, Dragonfly, Habitable Worlds, OSIRIS-REx. Anytime we get an opportunity to study something up close, looking at what caused life to actually form here on Earth. And then, you know, discovering the secrets of the universe, unfolding the universe kind of one galaxy at a time, studying it close up for the benefit of everybody. And to finish with my sort of initial thought, you know, we make all of our data completely public. We are, you know, we believe in open science. We want to make sure we're sharing, and we are doing this for the benefit of the nation and for humanity itself. Thank you so much.
So we are now open, maybe one question because of the time, so feel free to raise hand.
Yes.
Hey there, got a question over here. Thank you so much.
Well, first, thank you very much for that inspiring talk. Obviously, we're in a moment of lots of questions and transition in the space science community. And one of the things that I've never heard well articulated is how should we think about how much we're spending on space science, right? Why shouldn't it be twice as much as we spend right now, or why shouldn't it be? So that's the one that we all are here going to clap for. You know, why shouldn't it be half as much, which is what's being considered? But how do you articulate to the public the value and the specifics of what is the appropriate level of investment? It seems like we've come to sort of a political compromise that's lasted, but I've never heard anybody articulate how they justify the specific numbers. So thank you.
Yeah, that's a tough question to answer, because obviously I don't pick my number, and I probably would be applauding like Erica just did for you know, bigger budgets, because we always want to do more. But the thing is, we will always rise to the budget. So if you double my budget, I will just do more. And there are so many great ideas. There are, you know, that obviously there are always going to be people ready to do more. We can also adapt to the different environments. I mean, there, you know, obviously there is a nation goal to reduce our national debt. It is a great goal. I mean, there's nothing wrong with that goal. It's a great goal. And what I'm doing is I'm figuring out NASA science in this new environment. And so, you know, you pick your priorities and you go for your priorities. Our priorities are clearly, with this administration, are, you know, a sustained presence on the moon, crewed mission to Mars. I can tell you all of the things that you need to know before you send humans to Mars. I can, you know, and we need to have a science program that supports that really, really vital goal. We want to have a sustainable infrastructure here on Earth. We need to be able to predict space weather. We need to do it a lot better than we can do it now, because everybody relies more and more on technology. If you have astronauts that are going to be out in the solar wind, you want to be able to protect your astronauts. And so for me, it's not so much about justifying the number itself. It's about ensuring that we're doing impactful science that really feeds benefit into the nation, whether it is these incredible technology demonstrations, these technology advancements. And, you know, I mean, I mentioned we have hundreds of them from James Webb that are just incredible that you didn't know you needed. I mean, you can go back to the Apollo days and talk about, you know, the fact that we did this sort of crushable in the lander, in the return capsule, this crushable material that we all, you know, you all enjoy a comfortable landing most of the time on a plane because we've got that's memory foam, you know, and so many things come from the research that we do, and they are really led. We talk sometimes about NASA science as a pathfinder for space exploration. You know, the first powered flight over another planet is the Ingenuity. Beautiful Ingenuity helicopter. That's, you know, the first time that we've left the solar system, the first time that we've, you know, we've peered into the depths of time in the universe. Things that actually are driving technology, innovation, and fundamental science research. So I know I didn't answer your question because I'm, you know, again, I don't set my own number. I am grateful for every penny that we get, and my commitment is always to do the absolute best science that we can for whatever resources we have. Thanks.